Hello students, welcome to the class. So in the previous class, we have discussed about hydrides. So what are hydrides? Hydrides are, in simple terms, they are said to be an ion of hydrogen. Yes, and we have seen the types of hydrides. There are three types of hydrides. First one is ionic or saline hydrides, salt-like hydrides. We have also seen the properties of saline or ionic hydrides. Moving to the next, that is covalent or molecular hydrides. So what do we mean by covalent or molecular hydrides? These are binary compounds of hydrogen with non-metals belonging to P block. So saline or ionic hydrides, they belong to S block. They combine hydrogen combining with S block elements. Whereas non-covalent or molecular hydrides, they belong to P block. They are binary compounds again. Binary stands for two. For example, NH3, see two atoms are involved, two different atoms. Okay, total number there are four. CH4, carbon and hydrogen, H2O, hydrogen and oxygen, HF, hydrogen and fluorine. So these are called what? They are called covalent or molecular hydrides. They are mostly volatile compounds. So covalent or molecular hydrides means hydrogen, yes, hydrogen, it forms molecular compounds with P block elements. Yes, you can use any P block element. It might be boron, it might be carbon, it might be nitrogen, it might be oxygen, it might be fluorine, it might be silicon, it might be phosphorus. See, I hope you are recalling what are P block elements. It might be sulfur, it might be chlorine, it might be gallium, it might be germanium, it might be arsenic, it might be antimony, Sb, it might be bromine, it might be indium, it might be tin, Sn, it might be strontium, that is Sb, tellurium, then iodine, then thallium. You may pick lead, or it might be astatine. So with any of these compounds, with any of these elements, when hydrogen combines, it forms a covalent or molecular hydrides. Covalent or molecular hydrides. Yes, so covalent or molecular hydrides it forms. So common examples of these covalent or molecular hydrides, it includes CH4. Then you can have ammonia, NH3. Just now we have seen. It might be H2O. It might be HF. It might be HCl. Yes, it might be HBr. These are all the common examples. PH3. Yes, so these are all molecular hydrides. Okay, so the stability of these hydrides, it decreases down the group. So stability of molecular hydrides decreases down the group. That means as you move down the group, the stability decreases. Therefore, if I want to write the order for certain groups, say group 15 elements, nitrogen hydrides, then first comes NH3. So this is more stable thermally. Then below nitrogen comes phosphorus, which is more stable. Below phosphorus comes arsenic, which is more stable than phosphorus hydride is more stable than arsenic hydride. Arsenic hydride, which is more stable than strontium hydride. Strontium hydride, which is more stable than bismuth hydride. So as you move down the group, the stability of the hydrides decreases down the group. Yes, stability decreases. Yes, in a period, if you see, the stability increases with increasing electronegativity. So in a period, as you move across the period, the thermal stability of hydrides, these hydrides, it increases with increase in electronegativity. As electronegativity increases, it increases. Therefore, if I give you CH4 is there, then carbon, after carbon next comes nitrogen, NH3, then comes oxygen, H2O, then comes HF. So which is least stable here? The least stable is CH4 because it is less electronegative compared to all. So this order follows this. So HF is most stable, thermally stable. So across the period, the thermal stability of a covalent or molecular hydrides, it increases. It increases. Down the group, it decreases. So across the period, it increases, and down the group, it increases. So this is about molecular hydrides. They are classified further. They are classified as electron deficient molecular hydrides. So electron deficient means what? Electron poor. So the molecular hydrides in which a central atom does not have octet are called electron deficient hydrides. For example, so we have types here. In molecular hydrides, the first type is electron deficient, or you can say electron poor molecular hydrides. Yes, electron poor or electron deficient molecular hydrides. For example, you take boron hydride. So if you take boron hydride, what is the octet configuration? Oh, sorry, what is the dot structure for boron? Boron has 3 electrons in its outermost shell. So boron will share its 1 electron with 1 electron of hydrogen everywhere. And you can see here, with sharing by forming a covalent bond, all the hydrogens have completed their duplet. All the hydrogens have completed their duplet. But what about boron? Boron is what? Boron has completed it has only 6 electrons. So boron is what here? It is the central atom. It is the central atom for this molecule. And this central atom is electron deficient. It is electron deficient. It is poor of electrons. It has why it is electron deficient? It does not contain octet electrons, octet number of electrons. Therefore, I call it as electron deficient molecular hydride. One more example, the best example what I can quote here is, it is B2H6. B2H6 is called diborane. It is called diborane. Yes. So if you look at the structure of B2H6, this is electron deficient molecule. It is not having it is not having 8 electrons to the central atom. Diborane, I can represent it as boron, and here boron. Yes. So two boron atoms, and this boron is linked to 2 hydrogens here. It is linked to 2 hydrogens here. So B2H6, the remaining 2 hydrogens, they form the bridging between 2 boron atoms. So actually, see, when we talk about the 2 atoms, they share 2 electrons, right? So here it is duplet, here it is duplet, here it is duplet, here also it is duplet. But when you observe for bridging hydrogens, here it is not. So here I can say it is 2 atoms. So it is 2 atoms. Or you can say 2 center. So there are 2 atoms and 2 electrons. Correct? So here there are 2 electrons. Similarly here also 2 center, 2 electron. 2 center, 2 electron, 2 center, 2 electron. BH bonds there. But if you look at bridgings, they are 3 centered, but 2 electrons only. Here there is 1 electron, here there is 1 electron. Here there is 1 electron, here there is 1 electron. Such 2 BHB bonds we have. So this is deficient of electrons, 2, 4, 6. So this boron is having only 6 electrons, and this boron is also having only 6 electrons. So it is what? It is electron deficient molecule. Therefore, we say these electron deficient or poor polar molecular hydrides, they act as Lewis acids, which are electron acceptors. Electron acceptors. They act as Lewis acids. So these are what? These are electron deficient poor molecules, as we discussed. Yes. So electron deficient poor molecules, central atom does not have octet electrons, octet of configuration. Electron precise hydrides. Precise means what? Yes, they have complete octet. So here, those hydrides in which the central atom has its octet complete. Central atom has its octet complete. So they are called electron precise hydrides. Electron precise hydrides. Molecular hydrides. Okay. So electron elements of group 14 especially. So which group? Elements of group 14. They form these type of molecular hydrides. Elements of group 14, they form these molecular hydrides. Special example is your CH4. So this is what this is, molecular or covalent hydride, which is precise, having correct number of electrons. Carbon, it is having 4 valence electrons, and each hydrogen will contribute, will share one electron, and therefore the duplet of hydrogen is being satisfied everywhere, and the octet of carbon is also satisfied. Octet of carbon is satisfied. You can see here. So they have electron precise, correct number of electrons are there. Correct number of electrons. And since when you move down the group, carbon, silicon, germanium, arsenic, so when you move down the group, bond length goes on increasing. Bond length increases down the group. Down the group. Yes, bond length increases. So therefore stability decreases. Stability decreases. These are called electron precise molecular hydrides, especially group 14. Group 14 hydrides are electron precise molecular hydrides, and their geometry is what? Their geometry is tetrahedral geometry. Tetrahedral geometry. Third type of hydrides is electron rich hydrides. Those metal hydrides which contain lone pairs of electrons. They don't have, I am not saying that they have more than 8 electrons. No, students, they have 8 electrons only on the central atom. But since they have lone pairs of electrons, they become electron rich hydrides. They become electron rich hydrides. So that is the third type. So what is the third type? Electron rich molecular hydrides. Electron rich molecular hydrides. So what do we mean by electron rich molecular hydrides? Electron rich molecular hydrides means they have one or more lone pairs. They have one or more lone pairs. And I hope you know, remember what are lone pairs? They are unbonded electrons. They are non-bonded, unbonded electrons. For example, if you see NH3 molecule, yes, if you see H2O molecule, if you see HF molecule, these are all what? They are electron rich molecular hydrides. For example, nitrogen, it is having 5 valence electrons, but out of 5, 3 are involved in bonding. With what? With hydrogen. Such that all the hydrogens have completed their duplet. Hydrogens have completed their duplet, whereas nitrogen also has completed its octet. But why they are called electron rich? Because nitrogen in ammonia has one lone pair. Looking at next example, H2O, if you look at oxygen, it is having 6 electrons in its outermost shell. Yes, 1, 2, 3, 4, 5, 6. It will involve in bonding with one electron, so that hydrogen completes its duplet. This hydrogen also completes its duplet, and oxygen has completed its octet. See here, it is also having 8 electrons, not more than 8. But you can see there, oxygen has got 2 lone pairs of electrons. So it has 2 lone pairs of electrons. Similarly, last example, hydrogen fluoride. Fluorine has got 7 electrons in its outermost shell, and 1 electron is involved in forming bond with hydrogen, such that hydrogen has completed its octet, duplet, and fluorine also has completed its octet, but fluorine here has got what? It has got 3 lone pairs of electrons. 3 lone pairs of electrons. Therefore, we call these as electron-rich molecular hydrides. So, electron-deficient or poor molecular hydrides means what? They have less than 8 electrons in the outermost shell. Example, diborane, boron hydride, diborane. Boron hydride, this is diborane. See here, BH3 twice is B2H6. So these are electron deficient or poor molecular hydrides. Then we have electron precise, especially group 80C 14 elements show this such type of hydrides, electron precise hydrides. They have octet number of electrons on the central atom. Next is electron rich molecular hydrides. They also have octet number of electrons on the central atom, but the difference is that electron rich molecular hydrides contain 1 or more lone pairs of electrons. Ammonia, 1 lone pair, water, 2 lone pairs, and HF, hydrogen fluoride, 3 lone pairs of electrons. So NH3, PH3 has 1 lone pair, H2O, H2S have 2 lone pairs, or HF, HCl, they have got 3 lone pairs of electrons. Yes, so systematic names of molecular hydrides. See, when you are writing the names of these molecular hydrides, they are obtained from the names of the elements. For example, if you want to say the name of, let me take this example. if you want to say the name of PH3, so the name is obtained from the name of the element and suffix ANE you add. You add the suffix ANE. Like for example, this PH3 is called phosphane. It is called phosphane. Yes, another example, H2O. Do you know what it is called? Water is the common name, most commonly used name, but it is called oxidane. It is called oxidane. NH3, we call it as ammonia. Yes, ammonia itself is the IUPAC accepted name, but here we call ozane. Ozane. So these are the names, common, most commercially used names: phosphane, oxidane, ammonia, oxane, ozane. I'm sorry. Yes, ammonia is ozane. Yes, so this is about electron deficient molecular hydrides, electron precise molecular hydrides, and electron rich molecular hydrides. Third type of molecular hydrides. So first type is what? Ionic or saline molecular hydrides. Second type is what? Molecular or covalent hydrides. And third type is metallic or non-stoichiometric hydrides. Usually ionic hydrides are stoichiometric, whereas metallic hydrides are non-stoichiometric. So these hydrides are also known as interstitial hydrides. Transition metals of group 3, like example scandium, group 4 titanium, group 5 vanadium, form metallic hydrides. In group 6, chromium alone has the tendency to form chromium hydride. Metals of group 7, 8 and 9 do not form hydrides. This is called hydride gap. See, when we speak about transition metals have they come into how many groups? They come from group 3 to group 11, right? They come from group 3 to group 11. So here what is said, group 3, 4, 5, they form metallic hydrides. Yes, they form metallic hydrides. Group 6, in group 6, all group elements of 3, 4 and 5, group 3, group 4 and group 5, they form all the groups, all the elements which come in this group, they form metallic hydrides. In group 6, only chromium forms a chromium hydride, CRH. Group 7, 8, 9, they do not form any hydrides. Again, group 10, 11 form the hydrides. So 7, 8, 9 do not form hydrides. And which elements? For example, if you want to see, here scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and group 12, zinc. Yes, so here manganese, we don't have any hydride of manganese, we don't have any hydride of iron, we don't have any hydride of cobalt. So this is called, they do not form any hydrides. Therefore, this region of the periodic table, it is known as what? It is known as hydride gap. Hydride gap. It is known as hydride gap because it does not form. Here in these groups, they do not form any hydrides. So most of the group 7, 8, 9 do not form any hydrides. This region of the periodic table from group 7 to group 9, it is called hydride gap. Examples of these interstitial hydrides. Example of these interstitial or non-stoichiometric hydrides is scandium hydride, SCH2. You can have, then you have yttrium hydride, YH2, YH3 also you have, wherein Y state changes from +2 to +3. Then lanthanum hydride, lanthanides, they also form hydrides. Then we have titanium hydride, TiH2. You can have zirconium hydride, ZrH2. Then hafnium, HF hydride. Yes, all these are elements of transition elements. Vanadium hydride. Then you have nobelium hydride. Then nobelium hydride of type NbH also you have. Then thallium hydride. So these are all examples. Out of this, these are D block elements. The F block elements, they form hydrides of limiting composition. Either they form MH2 or they form MH3. Okay, all these hydrides are non-stoichiometric. Composition is not fixed. They have variable composition. Yes, for example, zirconium hydride, I represent it as X, wherein this X might vary from 1.30 less than, X is less than or equal to 1.30 and X is 1.75, more than or equal to 1.75. So it is non-stoichiometric. It is non-stoichiometric. You can see here. Latest study shows that nickel, palladium, cerium, actinium are interstitial in nature. This means they can occupy hydrogen atom in interstitial sites, vacant sites. The hydrides are generally non-stoichiometric and their composition varies with temperature and pressure. For example, see, titanium hydride, like how I've written chromium hydride H1, here it is 1.73. Cerium hydride, 2.7. Lanthanum hydride, 2.8. Yes, so metallic hydrides can be used to store hydrogen, especially in cars working on fuel cells. Especially to store hydrogen, we use this. So these hydrides have metallic lock and their properties are closely related to those of parent metal. They are strong reducing agents in most of the cases due to the presence of free hydrogen in the metal lattice. Free hydrogen is present in the metal lattice. Therefore, they are strong what? They are very strong reducing agents. They are very strong reducing agents. Yes. So this is about metallic hydrides. Yes. Okay. Non-stoichiometric hydrides are what? Hydrogen deficient compounds formed by reaction of dihydrogen with a D block and F block elements. So non-stoichiometric means what? They are metallic hydrides. So they are hydrogen deficient compounds. They are formed by the reaction of H2 with D block elements like scandium hydride we have seen so far, and F block elements like lanthanum hydride, actinium hydride, thorium hydride. These hydrides do not follow law of constant composition. What does law of constant composition says? You take any compound, whether it is naturally occurring or artificially prepared. Yes, they will have the simple whole number ratio by mass for the combining atoms. Yes, but here if you see, is it a whole number ratio? Lanthanum is to hydrogen. If you see here, they have given LaH 2.87. So what will be the ratio? It is 1 is to 2.87. It is not a whole number ratio. Ytterbium hydride, if you see, it is 1 is to 2.55. It is also not constant composition. Titanium hydride, it varies. In some cases, it is titanium hydride 1.5. In some cases, it is titanium hydride 1.8. Is it a simple whole number ratio? 1 is to 1.5 or 1 is to 1.8 is a simple whole number ratio or what? No. So it does not obey non-stoichiometric hydrides. They do not obey the law of constant composition. The law of constant composition. Alkali metals, they form stoichiometric hydrides. They are also called what? Ionic or saline hydrides. These hydrides are ionic in nature. Hydride ions, they have comparable sizes around 208 picometers with alkali metal ions. Hence, strong binding force exists between the constituent metal and hydride ions. As the result, stoichiometric hydrides are formed. Isotopic, moving to the next concept. So what all we discussed? Under hydrides, we have seen there are 3 types of hydrides. Yes, hydrides are totally different forms of hydrogen exist. First form of hydrogen is what? Atomic hydrogen. Next form of hydrogen is nascent hydrogen, newly born hydrogen. Then we have ortho and parahydrogen. If the nuclei are spinning in same direction, it is ortho. If they are spinning in opposite direction, they are para. Then we have hydrides. Under hydrides, we have 3 types: ionic or saline hydrides. Between S block element metals and hydrogen, it is ionic or saline. Then we have seen molecular or covalent hydrides. Between P block elements and hydrogen, it is molecular or covalent. In that, we have 3 types. Electron-rich molecular hydrides means what? They have octet, but there are 1 or more lone pairs. Then electron-precise molecular hydrides, they have correct number of 8 electrons on the central atom. Especially group 14 show this type of molecular hydrides. And then we have electron-deficient molecular hydrides, wherein what is there? They do not have 8 electrons on the central atom. So best example for electron deficient molecular hydrides is diborane B2H6. Then how do we give the names? We use the suffix ane, phosphane PH3, oxidane H2O, ozane NH3. Yes. Coming to the next one, that is isotopic effect. See, we have understood regarding what is isotopes. What are isotopes of hydrogen? Isotopes means what? They are atoms of same element. So atoms of same element having same atomic number. So when they are atoms of same element, they have same atomic number, but different mass number. Correct. And we also know that these isotopes, they differ in what? They differ in number of neutrons. Therefore, atomic number differs. Correct. So when we speak about isotopes of hydrogen, yes, which are the isotopes of hydrogen? We have protium, 1H1, or you can write it as 1P1. We have deuterium, which we write it as 1H2. Then we have tritium, which we write it as 1H3 or 1D2, 1T3. Yes. Okay. Atomic numbers are same. If you see mass number, which is denoted as A, it is 1, it is 2 here, and it is 3 here. Relative abundance, as I have said, this is the most abundant, 99.985%. This is least abundant, less abundant, 0.015%, and this is least abundant, say around 7 into 10 raised to minus 15% it is. Okay. Out of all the three, tritium is radioactive. This is radioactive, emits radiations on its own. If you look at the physical constants of this protium, deuterium, and tritium, molecular mass of protium is 2.016. Molecular mass of protium, it is 2.2, we take it as 2 unified mass. If you take deuterium, that is 1D2, it is 4. If you take tritium, 1T3, it is 6. Melting point, so this is mass. Melting point, if you see, protium, if you see, that means if you take molecules of this, okay, hydrogen molecule, deuterium molecule, tritium molecule. Melting point of hydrogen molecule is 13.8 Kelvin. Of deuterium is 18.7. Tritium is 20.63. Similarly, boiling point, if you see, it is 20.4. Here, deuterium is 23.9 and tritium is 25.0. Okay, so these are melting point, boiling points. What I'm saying, these are all physical constants. Bond energy, especially bond energy, if you see, the hydrogen H2, it is 435.9 kilojoules per mole. Deuterium, it is 443.4 kilojoules per mole. Tritium is 446.9 kilojoules per mole. So with all this, what do we mean by isotopic effect? In general, chemical properties of the isotopes are same, but there exist quantitative differences among them. Especially reaction between hydrogen and chlorine, it will give what? It will give HCl. And if you take deuterium and chlorine, it will give D2Cl. Okay, so if you see, the reaction between hydrogen and chlorine is 13 times faster than between deuterium and chlorine. Yes, under same conditions. Such differences, quantitative differences in chemical properties, which are due to, so the differences in the chemical properties, which are due to the difference in what? Difference in the mass number of the isotopes is known as isotopic effect. Yes, so what do we mean by isotopic effect? Difference in chemical properties. Difference in chemical properties due to difference in what? Mass number. It is of isotopes. Mass number of isotopes is called what? Due to difference in mass number of isotopes, it is called isotopic effect. What it is called? Isotopic effect. Very important. Yes, isotopic effect. That is found in the isotopes of hydrogen. Yes, I gave you the example also. Moving to the next concept, that is compounds of hydrogen. Hydrogen combines with the oxygen and forms H2O, that is water, correct? So water is what? It is a chemical compound, or you can say a chemical substance with chemical formula H2O. One molecule of water, if you see, it has got 2 atoms of hydrogen and one atom of oxygen. And how they are bonded? They are bonded to two hydrogen atoms. They are covalently bonded to single oxygen atom. We have discussed this in hydrogen bonding theory also. Yes, we have discussed it in hydrogen bond. So oxygen, it is having 6 electrons in its valence shell. One electron of oxygen atom, it shares with hydrogen. Another electron is shared with hydrogen, and it forms a covalent bond, OH covalent bond, OH covalent bond, wherein hydrogen have completed their duplet and oxygen has completed its octet. So this is example for what? Electron rich molecular hydride. It is example for electron rich molecular hydride. Molecular hydride. Correct? So it is electron rich molecular hydride. Fine. So since there are two lone pairs on hydrogen, what happens? There will be, according to VSEPR theory, so there are lone pair repulsions, and also lone pair bond pair repulsions, and also bond pair repulsions, because of which this structure will become like this, a bent structure for water. And there are two lone pairs of electrons. Correct? So water is what? So here water, it is nothing but it is oxide of hydrogen. It is oxide of hydrogen. And just now we have seen, when we were discussing electron rich molecules, what it is called? It is called oxidane. It is called oxidane. Correct? So water is oxide of hydrogen. It is an important component of animal as well as vegetable matter. Okay. Water constitutes around 65% of our body. So it is very important to keep ourselves hydrated. And it is the principal constituent of the Earth's surface. Yes, most of the Earth's surface is covered by water, right? So a glance of Earth taken from space will depict its blue. Why? The blue color is actually water. Major part of the Earth is covered with water. We need water for almost everything. Drinking, bathing, domestic purpose, cooking, vegetation, yes, agriculture. We should know about the properties of water. 65% of human body is composed of water. Water is essential for the survival of life on the earth. And water is distributed unevenly on the earth's surface. It forms a major solvent and dissolves almost every polar molecule. Therefore, water is called what? Water is called as universal solvent. It is called as universal solvent. Structure of water. Yes. In gas phase, it is a bent molecule with HOH bond angle 104.5 degrees and OH bond length of 95.7 picometers. It is highly polar in nature. Its orbital picture is also shown below. See, when we speak about the structure of water, just now we discussed that water is having what? We have seen here, it is formed by covalent bonding. Correct? It is formed by covalent bonding. Water is a simple molecule consisting of one molecule of oxygen atom bonded to two atoms of hydrogen. Yes. But if you look at the polarity, electronegativity of oxygen atom, because of a higher electronegativity of oxygen atom compared to hydrogen, the bonds become, OH bonds become polar. Therefore, it is an example for polar covalent compound. Yes. So it is an example for polar covalent compound. Okay. So the oxygen atom attracts the shared electrons of covalent bonds to a significant greater amount than hydrogen. As the result, what happens? What happens here? So since oxygen attracts the shared pair of electrons towards itself, as the result, oxygen will accumulate. It will acquire partial negative charge. and hydrogen will acquire partial positive charge when I speak about this bond. In this case, oxygen will acquire partial negative charge and hydrogen will acquire partial positive charge. So the molecule adopts a bent structure. The reason why it adopts a bent structure is we know that in case of water, oxygen is sharing only its 2 electrons to 2 hydrogen atoms, and there are 2 electrons, 2 pairs of electrons which are free, and those non-bonded electron pairs are called what? Electron pairs. They are called what? Lone pairs. Yes. So oxygen atom in water molecule has 2 lone pairs of electrons. Therefore, according to valence shell electron pair repulsion theory, there is maximum repulsion caused by lone pairs, 2 lone pairs, and which is more than lone pair bond pair repulsions, which is still more than bond pair repulsions. Because of this, the water molecule will not have linear structure because of 2 lone pairs. So it is a molecule of type AB2 and L2. So 2 bond pairs and 2 lone pairs. Therefore, it is having what structure? It is having bent geometry. And since it is having bent geometry, when you look at the bond angle of HOH, bond pairs we have to look at the bond angle. It is 104.5 degrees. 104.5 degrees. And oxygen atom is what? Oxygen atom in water molecule, it is sp3 hybridized. Yes, I hope you remember how to calculate hybridization, right? Half V plus M minus C plus A. So half V is how much? Valence electrons on oxygen are 6. It is bonded to 2. 8 by 2 is 4. So if H is equal to 4, what is the hybridization? It is sp3. So though it is having sp3 hybridization, expected geometry is tetrahedral and bond angle is 109.5. But it is not so because of presence of lone pairs. So the bent shape or inverted V of water molecule is critical here because there are 2 polar OH bonds. Yes, and if you look at the dipole moment, if we speak, they both are in same directions. Yes, so and even the dipole moment is because of these lone pairs also. They also contribute dipole moment, and resultant dipole is shown like this. So water molecule, it is polar molecule as the electron density is found around more electronegative oxygen atom. Yes, more electronegative oxygen atom. Correct? So if you look at the dipole moment, there are 2 polar bonds, that is 2 OH bonds, which are polar in nature. Therefore, what happens? The net dipole moment, it will have resultant dipole. And the dipole moment of water is how much? So in water molecule, the electrons are localized around oxygen atom because of more electronegativity. So presence of lone pairs also add to the dipole moment. Therefore, the individual bond dipole moments do not cancel out. Instead, they add up. So there are bond dipoles and even there are lone pair dipoles. So dipole moment comes out to mu. It is denoted as mu. It is 1.85 d by. Yes. So net dipole moment in water molecule is 1.85 d by, or 1.84 in some of the cases. So you can see here OH bond length is 95.84 picometers. Here also it is 95.84. Bond angle is 104.5. And here you can see partial charges on oxygen and hydrogen. Yes. Here, this is the explanation for dipole moment. Yes. So here towards more electronegative atom, and there will have resultant dipole, and the resultant dipole is 1.84 d pi. Orbital diagram of H2O. You can see here, these two are what? So these are sp3 hybridization, means there are 4 sp3 hybrid orbitals. So this is one sp3 hybrid orbital. This is one sp3 hybrid orbital. This is one sp3 hybrid orbital and this is one sp3 hybrid orbital. Here there are one electrons, and in case of these two there are lone pairs, 2 electrons, correct? Excuse me. So this the two sp3 hybrid orbitals of oxygen will overlap axially with s orbitals of hydrogen to form two OH sigma bonds. And remaining two contain lone pairs. They are not involved in hybridization. They are not involved in bonding, but they contribute to the structure. Expected geometry is tetrahedral, but because of lone pair repulsions, the geometry comes out to bent shape. And this is the bent shape. These are what? Lone pairs. And here the bond angle comes out to what? The bond angle comes out to 104.5 degrees. Yes, water in crystalline form. Ice is what? Ice is the crystalline form of water. Ice is the crystalline form of water. Okay. Atmospheric pressure, ice crystallizes in hexagonal form. You can look at the structure there. I've shown there. Yes. So ice crystallizes in the hexagonal form. At low temperature, it condenses to cubic form. Density of ice is less than that of water. Therefore, ice cubes float on water. See, this is studied under phases of water. It is studied under phases of water. Similar to many other substances, water can also take numerous forms. Its liquid phase is the most common phase of water on earth. It can also, and that is generally meant by the word water, liquid form. Solid phase is what? Solid phase is ice. The solid phase of water. Yeah. Here we'll take it out. Solid phase of water is called what? It is ice. Yes. So the solid phase of water is known as ice, and commonly this takes the structure of hard amalgamated crystals. Similarly, like amalgamated crystals, like ice cubes we say. So if you see ice cubes, they exist like this, correct? They exist like this. Okay. So unlike most other substances, water is a solid form, that is this ice, it is less denser than its liquid form. The reason is in gaseous, if you look at this phase, it exists in hexagonal packing in crystalline state. In crystalline structure, ice exists in hexagonal packing. Hexagonal packing. Yes. Therefore, that lattice contains more space. Because of hexagonal packing, it contains more space than the whole molecules are in liquid phase. Therefore, what happens? Naturally, if you see, as a naturally occurring crystalline inorganic solid with ordered structure, ice is considered to be a mineral. It possesses the regular crystalline structure having hexagonal packing. Yes, wherein based on the molecular structure of water, which consists single oxygen atom covalently bonded to two hydrogens, as I have shown it here. This structure. So this is oxygen, and small ones, what you are seeing, they are hydrogens. Oxygen, hydrogen. So these are water molecules taking the arrangement of hexagonal structure. Yes. So why ice is less denser than water? So density of ice as a function of temperature, if you see, the solid form of most substances, they are denser than liquid forms. Yes, so they are denser. Therefore, a block of given solid will generally sink in its corresponding liquid. But if you look a block of ice cube, it will float on liquid, that is water. It is because of the first thing, it is because of hexagonal packing, and second thing, it is because of the hydrogen bonding with water molecules. Okay. Coming to the next one, that is polarity of water molecule. Owing to the electronegativity difference between hydrogen and oxygen atoms and bent shape of water molecule, a net dipole moment exists. The figure indicates the partial charges of the atoms. So this is oxygen. So there are 8 protons, 8 neutrons, and there are 8 electrons. and 2 electrons. So 1 electron of oxygen, 1 electron of hydrogen forms a covalent bond. 1 electron of oxygen, 1 electron of hydrogen forms a covalent bond. And this there is bent structure. So it comes like this. It comes like this, correct? Therefore, because of electronegativity difference, oxygen being more electronegative, the electrons, the shared electrons, they are shifted, attracted more towards oxygen, due to which oxygen will have partial electron density more. Therefore, it will have minus charge, and this hydrogen will have positive charge in this bond when you consider. Similarly, these electrons are also attracted towards oxygen, so it will have partial negative charge and partial positive charge. So see here, weakly negative on oxygen, and weakly positive on hydrogen. So this is hydrogen. This is hydrogen. Yes. So this is the planetary model of water molecule. This is three-dimensional model. If you look at the model, it looks like this. And when you try to put distances between the two nuclei, it comes out like this. Structural formula of water molecule having two lone pairs on oxygen atoms. Clear with this? So this is polarity of water molecule. Because of this polarity only, polar compounds dissolve in water molecules. Polar compounds dissolve in water molecules because water is polar, and water is considered to be what? Most polar. So a water molecule can form maximum of 4 hydrogen bonds. Okay, formation of hydrogen bonds now. We know what is hydrogen bond, right? So what do we mean by hydrogen bond? Hydrogen bond. The bond formed between hydrogen and most electronegative atoms, say fluorine, oxygen or nitrogen, we call it as hydrogen bond. When we talk about, since we are talking about water molecule, yes, I will write the structure of water molecule here. So this is hydrogen. Since in water molecule, this is having slight negative charges, slight positive charge. What happens? The hydrogen of one molecule weakly attracts oxygen of another molecule, because here also slight negative polarity is there. Oxygen of another water molecule. Similarly, this hydrogen weakly attracts oxygen of another water molecule. Here, there are two partial negative charges. So oxygen of this water molecule attracts hydrogen of another water molecule, and this oxygen, same oxygen, will attract hydrogen of another water molecule. So it is capable, water is capable of forming how many hydrogen bonds? This is 1, this is 2. So 2 hydrogen bonds with oxygen itself, and third and fourth, and 2 hydrogen bonds with hydrogen. So hydrogen bonding in water, so it can form how many? Maximum of 4 hydrogen bonds by accepting 2 hydrogen atoms and donating 2 hydrogen atoms. Although hydrogen bonding is relatively weak attraction compared to the covalent bonds within the water molecule itself. It is responsible for number of water's physical properties. One such property is its relatively high melting and boiling points. So if you compare water with its other elements of the group, see, it is forming bond hydrogen and oxygen is there. Oxygen belongs to group 16. If I write group 16 element, say H2S, then we have H2SE. So when I compare melting point of water with others, the melting point of water is extensively more than H2S, which is more than H2SE. The reason is what? It is because water forms intermolecular hydrogen bond. Intermolecular, between the molecules. So because of intermolecular hydrogen bonding, what happens is there occurs association of molecules. Yes, I don't say it is very strong. Hydrogen bond is weak compared to covalent bond. But since there is association of molecules, we need to break these bonds first. Then after breaking those bonds, the melting point, what will happen to the melting point? The melting point will increase. More energy is required to break the bonds. That increases the melting point. So if you consider the elements of group 16 combining with hydrogen, so extensively high boiling and melting points are seen for water. They are seen for water, right? So it is more energy is required to break hydrogen More energy is required to break hydrogen bonds between molecules in order to change to higher energy phase. Physical properties of water. Yes, before going to physical properties, we have one more water. H2O is our normal water. We have one more water called heavy water. Yes, what do we mean by heavy water? Chemically, heavy water is called deuterium oxide. See, isotopes of hydrogen. When a protium combines with oxygen, it forms water. If deuterium combines with water, oxygen, it forms D2O. This is called heavy water because deuterium is called what? Heavy hydrogen. Yes, it was for the first time discovered by Urey scientist. It is obtained, where it is obtained, deuterium oxide D2O, which is called heavy water. It is obtained in as a byproduct in some industries where hydrogen is produced by electrolysis of water. See, we do electrolysis of acidified water, right, to get hydrogen. So when we carry out electrolysis of acidified water to obtain hydrogen gas, during that process, as a byproduct, we get deuterium oxide. So heavy water, deuterium oxide, is used where? First point, it is used as moderator. It is used as moderator and coolant. Moderator and coolant in nuclear reactors. Very important applications in nuclear reactors. Second point, it is used in the study of mechanism of chemical reactions. It is used in the study of mechanism of chemical reactions. Mechanism of chemical reactions. This is second application of deuterium oxide. Third point, it is used as a starting material for number of deuterium compounds. Starting material for number of deuterium compounds. This deuterium oxide is being used. For example, I can show you here. Example is sulfur trioxide. When reacts with deuterium oxide, it forms D2SO4, which is called, see, H2SO4 is sulfuric acid. D2SO4 is called deuterosulfuric acid. What it is called? It is called deuterosulfuric acid. Even aluminium carbide, Al4C3, when it reacts with D2O, I'll tell you the balanced reaction itself, 12 molecules of D2O, it forms 3 molecules of CD4 plus it forms 4 molecules of AlDO3. CD4 is called as deuteromethane. Like how you have CH4, CD4 is called deuteromethane. It is called deuteromethane. Similarly, calcium carbide, CaC2, reacts with D2O, 2 molecules of D2O, to form C2D2 and CaOD twice. Calcium deuteroxide, aluminium deuteroxide. This is called C2O2 is called, like how you have C2H2 acetylene, you call it as deuteroacetylene. We call it as deuteroacetylene. So first application, what we said, it is used as moderator and coolant in nuclear reactors. It is used in the study of mechanism of chemical reactions. And third, it is used in preparation of various deuterium compounds like deuterosulfuric acid, deuteromethane and aluminium deuteroxide, or deuteroacetylene and calcium deuteroxide. So this is all about heavy water. In the next class, we will discuss about the physical and chemical properties of water and proceed with the next compounds of hydrogen. Hope you have followed the concepts explained today. Please practice the structures of water, ice, whatever it is, and all the other concepts also. Thank you.